Hi. We were looking at this graph, and I know it looks a little bit messy right now, but we were looking at this graph and trying to figure out about the energy in a spring. Okay, so I'm going to give you a little bit more information, but first, just to review, we saw that there's two variables that determine how much energy is in the spring. It's how hard or with how much force the spring is being pulled with, and the length that that string is being pulled. Okay, and so um, we have those two variables, and we said that for a spring, the energy in the spring is the uh, area that is under this graph right here, that is trapped between the line for the graph and the x-axis, okay? And so how do we find the area that is under that graph? Well, it's base times height times 1/2. That's the formula for a triangle. So we find the area of that triangle and we know the energy in the spring. All right, so that energy in the spring is going to be 1/2 times the force, which is the height, and times the length, which is the base. So height times base times 1/2 will give the energy in that spring. Okay, so now let's actually solve a problem. So let's find the actual energy that is in here. And this is supposed to be a 10 right here. It's a little bit hard to draw on this whiteboard. And so it's supposed to be a 10. So let's use this equation and find the energy that's in the spring. All right, so I'm going to go along on my whiteboard and I will write energy elastic equals 1/2 times the force, which is on the left-hand column. And let's try to figure out how much force that is right here. That's a 1 right there. And so, I'm sorry, that's a 10 right there. And so moving along right here, I think that is about, I'm going to say that that is about a 6 right here. It's about 6 newtons right there. And so I'm going to go back up here and I'm going to go ahead and write a 6. And I'm going to make sure I write the newtons, the force units. All right. And now let's go down to the bottom. And we can see that for the bottom here of the graph, the base of the graph, the length is 0.5. And so I'm going to go ahead and write that also up here. So I need to multiply by 0.5. Okay, oops, I forgot to write meters. And I need to write meters in my equation. All right. And so now my result is going to be 6 times 0.5, 6 times 0.5, which is 3, and then 3 times 1/2, which is 1.5. So my answer is 1.5. Now, what are my units? Well, newtons is the force, meters is the length, and so I'm going to write Newton meters here. That is the units. All right. We don't lose any units when we do an equation. We just keep them. We multiply them or divide them depending on what our equation says. So it's 1.5 Newton meters. Now, some of you may be saying, but I thought the units of energy was joules. And in fact, guys, this is a joule. A Newton times a meter equals a joule. All right, they're the same thing. All right, a joule is an abbreviation for a Newton times a meter. All right, and so you need to keep that in mind that if you end up with in an equation Newton times meters, you can write joules. But you can also, if you write joules, you can be thinking, well, that's 1 Newton of force times 1 meter of stretch. Okay, we're going to see this more than once, what a joule actually means. I want to do one more problem here. No, I'm not going to do one more problem. I'm just going to remind you guys that we could do the same equation here, but we could use a length of 1 meter and then maybe a force of 12. 12 times 1 meter times 1/2 would also give us the force under if we wanted to do this whole area.